The next unit is state variable analysis. Already I told you that it is extension of first unit. Extension of first unit. In the first unit, we have seen mathematical model of mechanical systems, electrical systems. How to represent the mathematical model in state space is called state variable method. What is the drawback in transfer function model? So far, we have seen only transfer function model. Transfer function, while finding transfer function, what we are assuming that zero initial conditions, zero initial condition. It means what? Suppose you are taking a mechanical system, it is at rest. The velocity is zero. Initially, its acceleration is zero. Its velocity is zero. It is at rest, like that we are taking. If it is electrical system, there is no voltage, no current initially, like that we are assuming. If we assume like that, the capacitor no voltage, in the inductor no current, like that we are assuming. That is initial conditions are zero, like that we are assuming, we are finding transfer function. The drawback is if you assume initial conditions, it's not possible to find the transfer function. That is the drawback with the transfer function method of representation. Second drawback is it describes only the relationship between input and output. What is the transfer function? T of S, G of S equal to Laplace transform of output by Laplace transform of input. That is the transfer function. K upon tau S plus 1, first order system. It is the relationship between input and output. Only two variables are involved. One input, one output. That's all. Suppose in a car, many variables are there. The engine temperature, car speed, engine temperature, and the fuel. How much fuel is reduced? How much fuel is flowing into the carburetor? So many things. How many fuel is injected into the engine? Like that, there are many variables are there. But in a transfer function model, that is SISO system, we are considering only output and input. In a car, how we modeled the speed versus acceleration, input acceleration. Like that we model. We cannot consider other variables in transfer function model. That is, this transfer function is limited to SISO system, single input, single output system. That is the drawback. And it is applicable only for time invariant system. Time invariant system. This is tau is constant. This tau is constant. Constant. The K is constant. K is constant. If you assume like that, then only you can find the transfer function. So it is time invariant. It is not time variable. Time invariant system. So these are the drawbacks with the transfer function model. That's why we are going to state variable model. In state variable model, you can consider, for example, in a MIMO system, if you consider MIMO system, how many inputs are there? M inputs are there. In this case, M inputs are there. How many outputs are there? P outputs are there. Outputs are there. P outputs are there. Y1, Y2, Y3, Yp up to. Inputs are U1, U2, U3, Um. You cannot represent this in transfer function model. You can take U1, you can find Y1. All other variables are disturbance like that. You can assume a system. The system is SISO system, and that one input, one output. That's all. Here in state space model, you can assume n number of inputs, n number of outputs. That is possible. If you represent that, then each state variable, each variable that you are considering, what are the state variables you are considering? X1, X2, X3, etc., Xn. Because it is nth order system. Therefore, n state variables will be there. If it is nth order system, n state variables there. If it is fifth order system, 5 state variables will be there. So the number of state variables equal to the order of the system. Each state variable, X1 is a state variable. For in a car example, X1 is speed of the car. X2 is engine temperature. X3 is how much fuel is at present there. Third one is That is also important. How much fuel is there? Also important. In a rocket system, if rocket is going up and up, the fuel is decreasing. Therefore, the weight of the vehicle, the weight of the rocket system is decreasing. Finally, it is went to orbit means what is the fuel? My fuel becomes zero. That's why we have to take that into account. In that case, you can consider weight of that fuel also. That is third variable. Then what is the amount of fuel injected? What is the velocity of fuel injected into the system? That also you can take another variable. Like that, many variables are there. It's a derivative of each variable. Derivative means what? Velocity. Velocity of x1, velocity of x2, velocity of x3, like that. That can be written as function of, all state variables, x1, x2, x3, x4, etc., xn, and all inputs. What are the inputs? How many inputs? The m inputs. u1, u2, etc., um. You can write as a function of x1 dot can be written as a function of x1, etc., xn, comma, u1, etc., um, like that we can write. x2 also can be written the same way, but it is another function, f2 function. xn can be written as another function, f1. If you write like this, then it is represented in state variable form. State variable form. Now, what is the definition for state variable? Here, the number of state variables here is n. That is the minimal set. You cannot find n minus 1 or n plus 1. That is not possible. You cannot find n minus 1. You cannot, if you take n minus 1 state variables, then if you take n minus 1, it is not, the system is not completely specified. The system is not completely specified. For example, the weight of the fuel is not considered, means the system is not completely specified. At any instant, you cannot completely specify the system because weight is reducing as the vehicle goes up. Here, vehicle, I'm saying that the rocket going up, the fuel is decreasing. That's why weight is decreasing. That's why you should consider weight of the fuel. Then only it is complete definition. Suppose you are leaving one variable, means the system is not completely specified. If you take additional variable, means suppose I'm adding two variables. For example, I'm finding the third variable as speed of a rocket you are taking. In addition, you are taking some other variable, say a combination of two variables, engine temperature and surface temperature added together. That is one variable. Like that, if you take means, you will get n plus 1. So, only n is possible. Prime variables, x1, x2, etc., xn, like that, you will get prime variables. If you find n plus 1, it is not prime. N minus 1, it is not completely specified. This is over specified. This is under specified. So you have to take n state variables. That's why it is called minimal set of variables. The number of variables equal to the order of the system. Number of variables equal to order of the system. Number of state variables equal to state variables equal to order of the system. It is nth order system, means n state variable will be there. What is the definition for state variable? The state of the system is a minimal set of variables, n variables, such that the knowledge of these variables at a t equal to t naught, initial time is t equal to t naught. No need to take t equal to 0. In transfer function model only we have to take t equal to 0. Here t equal to t naught, together with knowledge of the inputs at t greater than or equal to t naught. After t naught, I know all inputs. Then it completely determines the behavior of the system after t greater than or equal to t naught. After t, I am starting at t naught. At t naught, I know what are, after t naught, what are the inputs I am applying, I know. Then I can find the state of the system, x1 to xn, at any point. Then the x1 to xn are called state variables. The state of the system is minimal set of variables known as state variables, such that the knowledge of these variables are t equal to t naught, together with the knowledge of the inputs for t greater than or equal to t naught, completely determines the behavior of the system t greater than or equal to t naught. After t naught, it completely specifies the system. Now, let us take a third order system, g of s equal to, let us take the second order system or third order. Okay, let it be third order. S cube plus a s square plus bs plus c. What is the order of the system? Third order. So if you, what is the g of s? G of s is x of s upon u of s, where x of s is the output, u of s is the input. If you cross multiply, what you will get? Cross multiply k u of s equal to x of s multiplied by s square s cube plus a s square plus bs plus c. Or I can say that s cube means what? I want to write in time domain. K u of t. Time domain u of t. U of s becomes u of t. S cube means third derivative. D cube x by dt cube. This is s cube. Plus a s square means second derivative. D square x by dt square. Plus b dx by dt plus cx. So this is the differential equation. This is the differential equation. For that, we obtained the transfer function like that. So this can be written as in state space model. How I am writing? Let us see. Let us assume that x equal to x1. X equal to x1 as you are assuming. I am giving new variable name x1. X equal to x1. X is the output. X is the output. X is output. I am finding another output, that is state variable x1. X equal to x1. x1 dot equal to x2. I am writing x1 dot equal to x2. First derivative of first variable is called second variable x2. Second state variable x2. x2 dot equal to x3. I am defining like that. x3 dot equal to x3 dot equal to, since it is third order, that's why I'm stopping here. Otherwise, I can write like this continuously. I'm assuming that x1 dot equal to x2, x2 dot equal to x3, x3 dot equal to question. Here, this can be written as keep these d cube x by dt square one side and keep all other variables on the other side. What you will get? D cube x by dt square equal to k u of t minus a d square x by dt square minus b dx by dx by dt plus cx. Can I write like that? Huh? So d square x by dt cube minus, no, it is on the other side already. K u of t is on the other side, no? Yes, cx is minus. You are saying correct. Thank you. Minus cx. Minus cx. So now, what we assumed? X equal to x1. That's why we can write this as cx1. What is dx by dt? Minus b x1 dot. What is a d square x by dt square? x1 double dot minus k u of t equal to x triple dot. Am I correct or not? All are derivatives. We can write like that. X double triple dot of t equal to k u of t minus a x1 double dot b x1 dot c x1. But x2 equal to x1 dot. That's why I can write this as, I am writing c x1 as such, but x1 dot is x2. That's why b x2 I am writing. Can I write like that? X1 double dot can be written as x2 dot because x2 dot derivative of x2 dot is x1 double dot. X1 double dot. X2 dot, sorry. X2 dot is x1 double dot. Am I correct or not? Because x2 is what? X1 dot. If you differentiate one more time, you will get x2 double dot. So x3 dot is x1 triple dot. X3 equal to what? X2 dot. X2 dot equal to x1 double dot. That's why x1 triple dot is x3 dot. X3 dot equal to x1 triple dot. So now x is x1. Already we defined x is x1. Therefore, x1 dot can be written as x2. X1 double dot is what? X3. So minus ax3. ax3. Am I correct? X1 double dot equal to what? X1 double dot equal to x3. X1 double dot equal to x3. If you want to remove dot, you have to write one number ahead. That's all. X1 dot equal to x2. X2 dot equal to remove x3. Like that. You have to remember. But x2 dot can be written as x1 double dot. X1 double dot. X3 dot is x1 triple dot. X2 equal to x1 dot. So we can write k u of t. X triple dot. X triple dot. Now substitute here. The question mark can be substituted from here. Minus ax3 minus bx2 plus cx1. The left hand side you see all derivative. Right hand side you see all non-derivative. Right hand side only variable. Left derivative is only in the left hand side. That too first derivative only. So I wrote this third order equation. If you write in time domain, what you are getting is third order differential equation. Now I broken this into three first order equations. Three first order equations. Third order equation is split into three first order equations. What are the three first order equations? X1 dot equal to x2. X2 dot equal to x3. X3 dot equal to k u of t minus ax2 x3, sorry, ax3 minus bx2 cx1. That's all. So the third order equation becomes three first order equations. So if you put this in matrix form, x1 dot, x2 dot, x3 dot equal to, I am putting all these constants. What is the coefficient of, I am taking state variables outside, x1, x2, x3, state variable, plus input, another state variable. Input also I am writing separately. I will explain. U of t, k u of t. Here, what is the first equation? X1 dot equal to 0x1, 0, 1x2, 0x3. Second equation, 0x1, 0x1, 0x2, 1x3. Third equation, minus cx1, minus bx2, minus ax3. So I put this in matrix form. If you multiply, you will get these three equations. How to you will get in how to multiply these two? Take first row, first column. 0x1. This can be written as 0x1 plus x2 plus 0x3. This can be written as 0x1 plus 0x2 plus x3. The third equation, this can be put in matrix form. Here in the third equation, you are having plus 0 u of t plus 0 u of t. Here, k u of t. That's why here only we are having k. Here only you are having first two equations 0 u of t. I put this in matrix form. I put this in matrix form. Third degree equation, third order equation is written in matrix form. Written in matrix form. This is called state space representation. This representation is called state space representation. I am breaking the third order equation into three first order equations. Therefore, in the mathematics, you are having plenty of matrix manipulations. Plenty of matrix manipulations. All matrix manipulations can be applied to differential equation. All matrix manipulations can be applied to differential equations. That is the advantage of writing this into three first order equations. So a third order differential equation is written as three first order differential equations. So this is state space. If it is nth order, means what is the equation? Nth order equation. Nth order means T of S equal to K upon. How we will write Tn S power n plus, sorry, An S power n, An minus 1 S power n minus 1 plus etc. plus A naught. Like that you will write. If you write this in state model, you will get x1 dot, x2 dot, x3 dot, x4 dot, etc. xn dot, xn dot equal to, you will get A matrix. Here you got an A matrix, A11, A11, A12, etc. A1n. Here A21, A22, etc. A2n, etc. An1, etc. Ann. You will get n matrix elements. Here what you will write? Integral of this value. What is the integral of this state variable? State variables x1, x2, x2, etc. xn. You will write plus. You will write m input variables. M input variables. B11, B12, B13, etc. B1m, etc. Bn1, etc. Bnm. You will get a B matrix multiplied by U of t. This also many inputs. Say U1, U2, U3, etc. Um of t. So many inputs. This is a state space representation of nth order system. How many inputs? M inputs. M inputs. We can write these state variables in the outputs are P outputs we have seen. How many outputs we have seen? P outputs we have seen. How to write these P outputs? P outputs Y1, Y2, etc. Yn, Yp equal to a matrix. Here C matrix, that is x1, x2, x3, etc. xn plus the same D11, D12, etc. D1m, DNM, DNM. Here U1, U2, etc. UM. This is how many? Sorry, How many DPM? How many rows will be there? Only P rows. Here, X, C11, C12, etc. C1N, etc. CP1, CP2, etc. CPN. Here, D1, DPM. Here also DPM. What is the dimension of the C matrix? Number of rows equal to P by N. What is the dimension of this? Number of rows equal to P by M. What is the dimension of the state variable? N by N. What is the dimension of this? N by M. So dimension of A matrix is N by N. This matrix is called A matrix. A matrix. This matrix is called B matrix. This matrix C matrix, D matrix. Therefore, I can write the state model as X dot, capital X dot equal to A matrix multiplied by X plus BU. Like that I can write, where X is a state variable matrix. Y equal to CX plus DU. CX plus DU. This is output equation. This equation is called output equation. This equation is called output equation because it gives output. This is called state equation. State equation. Because it gives state variable. State equation. These two together is called state space model. State space model. State space model for the given mechanical system. You know the mathematical model of this. You know the mathematical model of this. What is the mathematical model of this? Write the state equations for a mechanical system. Mass is M, spring constant is K, applied force is F of T, the dashpot constant is B. We know the mathematical model. The displacement is X. Displacement is X. Therefore, the mathematical model is M d square X by dt square plus, here one end is fixed, other end is moving. Therefore, B dx by dt. Here also one end is fixed, other end is moving. Therefore, Kx equal to applied force F of T. This is the mathematical model of mechanical system. How to represent this in state space? There is no friction given for these wheels. That's why it's not taken into account. Friction-free wheels. We are assumed. Therefore, BR here, BR, another name for the B. We have to find the highest degree. We have to keep the highest degree in the left-hand side. In the third order, what we did, we keep the highest. We kept the highest degree in the left-hand side. We other variables to the right-hand side. The same way we have to write like that. So keep the d square x by dt square as one side. D square x by dt square equal to 1 by m f of t minus b dx by dt minus kx. The same way, we are assuming that x equal to x1, the output x equal to x1. x1 dot equal to first derivative of x1 is x2. x2 dot equal to, why we are keeping x1 dot equal to x2? What is the meaning of that? What is first order differential equation? If you write a dy by dt plus by equal to c. Can I write like that? C u of t. Dy. Keep dy by dt one side. Dy by dt one side. What you will get? 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u of t minus b dx by dt. 1 by a c u By. What is the derivative? This can be written as y dot equal to 1 by a c u of t minus b y. So this can be written as y1 dot equal to y1. So it is a first order equation. It is a first order equation. Simple first order equation is x1 dot equal to x2 is a first order differential equation. Another differential equation I am writing x2 dot equal to x3. Whether I have to write? No, because x2 dot already we know. We will replace this x by x1, kx1 minus. This is dx by dt is x1 dot bx1 dot f of t multiplied by 1 by m. This can also be written as f of t divided by m minus b by m. X1 dot equal to what? X2 minus kx1. Now we can write in state space model the x2 dot equal to minus b by m x2 minus kx1 plus f of t divided by m. K by m. That's all we got in state space model. What is the state space model in matrix form? It is second order. That's why x1 dot x2 dot equal to, what are the two variables? x1 x2 plus what is the input? U of t. F of t. Here, what is the first equation? Only x2 is there. 0, 1. Second equation, x1, x2 both are there. Minus k by m minus b by m. Here, this f of t is in second equation only, not in the first equation. A matrix is, in this case, this is A matrix, this is B matrix. We wrote in state space model. So in the examination, they may ask, they will give the mathematical model. You have to find as we did in first unit, but we have to convert this into state space model. This is the simplest sum representation of the system shown in figure. Obtain the state space representation of the system shown in figure. We know how to obtain the mathematical model for this. The forces acting on the mass m1 are Fm, Fb1, Fk1, Fb2 and Fk2 are the forces acting on m1. Similarly, forces acting on m2 are f of t, u of t, Fb2, Fk2, Fm2 are the forces acting on m2. Displacement in the first mass is x1, y1, and the displacement in second mass is y2. Therefore, the mathematical model is m1 d square y1 by dt square plus b1, one end is fixed, therefore b1 dy1 by dt plus k1 y1, and these are all acting between two masses. That's why plus b2 d by dt of y1 minus y2 plus k2 y1 minus y2 equal to 0. No applied force. That's why equal to 0. This is first equation. The second equation is m2 d square y2 by dt square plus b2 dy2 by dt plus k2, sorry, b2 d by dt of y2 minus y1, because both ends are moving, and k2 y2 minus y1 equal to applied force u of t. Applied force u of t. This is second equation. What is the order of the system? Here order is 4, because this is second order. This is another second order. 2 plus 2 equal to 4. Therefore, the given system is fourth order system. How many state variables will be there? 4 state variables will be there. 4 state variables will be there. We have to assign these state variables. First, let us assign x1 equal to y1. X1 dot equal to x2, that is equal to y1 dot. Similarly, x3 equal to y2, another state variable, and x3 dot equal to y2 dot equal to x4. So we assigned 4 state variables. We assigned 4 state variables. We have to convert this given equation. We have to convert this. We have to convert these two equations into state model. State model. That is the question actually, because we know how to obtain these two equations. The first unit we studied. Now we have to convert this into state model. So first thing is we have to find the order of the system. The order of the system is 4. Therefore, 4 state variables are there. 4 state variables are there. Now we are assigning the 4 state variables. X1 equal to Y1, because the first displacement is one state variable. Second displacement is another state variable. X1 equal to Y1, X1 dot equal to X2 equal to Y1 dot. That is, X2 is another state variable. Third state variable is Y2, X3 equal to Y2, X3 dot equal to Y2 dot equal to X4. So we defined 4 state variables. Now we have to substitute all these things in this equation and we have to find the model. Here, this is equal to what? Second derivative of y1 is x2 dot. Am I correct? Or x1 double dot. Or we can say that it is x1 double dot. x2 dot or x1 double dot, we can say second derivative, because x1 is y1, x1 double dot. This is what? This is y1 dot. Y1 dot equal to x2 or x1 dot. Y1 dot equal to x2 or x1 dot. Normally, we have to assign state variable, not derivative of state variable. Y1 is x1. This is x1. So y1 is x1. Y2 is x3. y1 is x1, y3 is x3. This is x1 dot minus x3 dot. That is x4, we can write this. x3 dot, that is equal to x1 dot is x2 minus x4. Now we'll convert, before converting this, the first equation can be written as m1 d square y1 by dt square equal to minus b1 dy1 by dt plus minus k y1 minus b2 d by dt of y1 minus y2 minus k2 y1 minus y2. Now substitute all these variables. D square y1 by dt square is, you can bring this, before doing that, we can bring this m1 to the right hand side. 1 by m1. Therefore, x2 dot equal to minus b1 by m1 dy1 by dt is x2. The right hand side, we should not write any derivative. We should write a, that's why we should not put x1 dot, we should put x2, because x1 dot equal to x2. Whether we have to substitute x1 dot or x2, we have to think, we have to substitute x2, because it is not, we should not substitute any derivative. Minus k by, this is k1. k1 by m1, y1 is x1, minus b2 by m1, b2 by m1. Derivative of y1 is x2 minus derivative of y2 is x4. Then minus k2 by m1, x1 minus x3, y2 is x3. That's all. So we converted the first equation in terms of first order differential equation. x2 dot equal to, group all x1 together minus k1 plus k2 upon m1 multiplied by x1. All x1s are grouped. x2s are grouped. Group all x2s minus b1 plus b2 upon m1 multiplied by x2. Group all x3 together plus k2 by m1 x3. Group all x4 together plus b2 by m1 x4. Already we have x1 dot equal to x2 one equation. For x2 also we got, this is equation A, this is equation B. From second equation we have to find the third. What is second equation? m2 d square y2 by dt square equal to minus b2 d by dt of y2 minus y1 minus k2 y2 minus y1 plus u of t. What is this can also be written as m2 y2 double dot equal to minus b2 y2 dot minus y1 dot minus k2 y2 minus y1 plus u of t. y2 double dot is x3 dot. y2 double dot means y2 dot. y2 dot equal to x3 dot. Therefore, we can write x3 dot equal to x3 dot equal to minus b2 by m2. y2 dot is x4. y2 dot is x4 or x3 dot or x4 minus b2 by m2. y1 dot equal to y1 equal to x1, y1 dot equal to x2 minus k2 by m2. y2 is x3 plus k2 by m2. This is plus because of 2 minus, that's why plus. k2 by m2, y1 is x1 plus u of t. So now this is equation B. Already we have one equation, x3 dot equal to x4. We have one equation, x3 dot equal to x4. Now put all together in matrix form, x1 dot, x2 dot, x3 dot, x4 dot. Equal to x1, x2, x3, x4 plus u is in the third equation only. U is in the x3 dot only. Therefore, we can put 0, 0, 1, 0 u of t. Here, what are the coefficients of first equation? x1 dot equal to x2. Therefore, 0, 1, 0, 0. x1 dot equal to x2. Then, this equation we have to consider. The coefficient of x1 is minus k1 plus k2 divided by m1. Minus k1 plus k2 upon m1. The second element is minus b1 plus b2 divided by m1. Minus b1 plus b2 divided by m1. This is second element. Third element, k2 by m1. k2 divided by m1. The fourth element is b2 by m1. b2 divided by m1. Here x3 dot equal to x4. This is 1. All others are 0. Here from this x3 dot we have to write. Sorry. x3 dot equal to x4. Correct one. x3 dot equal to. Here y2 double dot is x4. x4. I did wrongly. Am I correct? y2 dot equal to x4. y2 double dot equal to x3 dot. Sorry, this is y2 dot equal to x3 dot. x3 dot. Therefore, sorry, x4 dot or x3 double dot or x4 dot or x4 dot equal to, we have to find. Therefore, this is x4 dot. x4 dot. x3 dot equal to x4 and x4 dot equal to this. What is the coefficient of x1? k2 by m2. k2 by m2 plus What is coefficient of x2? b2 by m2. b2 by m2. What is the coefficient of x3? minus k2 by m2. Coefficient of x4 is minus b2 among m2. So this is A matrix. This is A matrix. This is B matrix. That is x dot equal to ax plus bu. Suppose you want to write output equation, means what are all outputs? Y1 and Y2 are outputs. Y1 and Y2 are outputs. Y1, Y2. These two are output equal to what you will get? Y1 equal to x1. Y1 equal to x1. Y2 equal to x3. Y2 equal to x3. Therefore, we can write 0. We can write 1, 0, 0, 0, 0, 0, 0. This is second row is x3. X3. Therefore, 0, 0, 1, 0. X1, X2, X3, X4. This is C matrix. D matrix equal to 0 in this case. In this case, D matrix is 0. Y1 equal to X1, that is the displacement. Y2 is X3, that's all. D matrix is 0 in this case. That's all about this sum. So we wrote in state space model. Circuit shown in figure obtain the state equations. The input voltage source is U of t and the output Y of t is taken across the capacitor C2. There are three energy storage elements, C1, C2, and L. That's why the number of state variables equal to 3. Let them be x1, x2, and x3. Let voltage across VC1 equal to x1, VC2 equal to x2 equal to y. The output also the capacitor voltage across capacitor. Let the current through the inductor be x3. That is PC1 equal to x1, comma VC2 equal to x2, and I1 minus I2 equal to x3. But I1 equal to C1 dVC1 by dt, that is equal to I1. That implies C1 dx1 by dt equal to I1, or C1 x1 dot equal to I1, first equation. Similarly, we can write C2 dVC2 voltage across capacitor equal to I2. That implies C2 dx2 by dt equal to I2, or C2 x2 dot equal to I2. That is second equation. Third equation is I1, that is C1 x1 dot minus C2 x2 dot equal to x3. This is third equation. We can write one equation based on KVL, that is U of t for loop 1. Current through this is I1, current through this is equal to I2. Therefore, U of t equal to, what is Kirchhoff's voltage law? Algebraic sum of potential drop and EMF equal to 0. Therefore, u of t equal to x1 plus what is current through voltage across inductor L d I1 minus I2 upon dt. This is VC1 plus L di by dt. But u of t equal to VC1 equal to x1, we assumed. VC1 equal to x1, we assumed. Therefore, this can be replaced by x1 L dx3 by dt. That is u of t equal to x1 plus L x3 dot. Therefore, x3 dot equal to u of t minus x1 divided by L. That is first equation. We got one equation. We can find, similarly, we can find for x2 dot also. We know that the third equation says C1 x1 dot minus C2 x2 dot equal to x3. So from this, we can say that we can find x2 dot. Similarly, if we consider the second loop, that is I2 loop, what you will get is L1 d by dt of I2 minus I1 plus R I2 plus VC2 equal to 0. So minus L d by dt of x3, because I1 minus I2 is x3, that's why I2 minus I1 becomes minus L d by dt of x3 plus R I2 plus VC2. VC2 equal to what? X2 equal to 0. Therefore, now we can substitute for I2. I2 equal to what? I2 equal to x2 dot, second equation. So if you substitute L x3 dot plus R x2 equal to what? C2 x2 dot plus x2 equal to 0. Therefore, we can find the equation for x2 dot. R C2 x2 dot equal to L x3 dot minus x2. That is equal to L. Already we know the expression for x3 dot, that is u of t divided by L minus x1 divided by L minus x2. So this L getting cancelled. Therefore, x2 dot equal to u of t minus u of t divided by RC2 minus x1 divided by RC2 minus x2 divided by RC2. This is the equation for x2 dot. Similarly, we have to find the expression for x1 dot. For that, let us consider the equation 3. That is C1 x1 dot minus C2 x2 dot equal to x3, or C1 x1 dot equal to x3 plus C2 x2 dot, that is equal to x3 plus C2. X2 dot equal to what? Already we know that we have to substitute here. U of t divided by RC2 minus x1 divided by RC2 minus x2 divided by RC2. Therefore, C2 getting cancelled. Therefore, x1 dot equal to x3 by C1 plus U of t R by RC1 minus x1 divided by RC1 minus x2 divided by RC. That is x1 dot. So we got x1 dot, x2 dot, and x3 dot. Now we can put all together in a matrix form. We got x1 dot, x2 dot, x3 dot. All equations together in matrix form. We got x1, x2, x3 plus U of t. The x1 dot equal to x3 by C1 minus x1 by RC minus 1 by RC1 multiplied by x1 minus 1 by RC1 x2 and minus 1 by C1. That is first row. Second row from here we have to get second row. What is coefficient of x1? Minus 1 by RC2. Coefficient of x2 is minus 1 by RC2 again. x3 is not there, that's for 0. U of t is 1 by RC2. 1 by RC2. Here 1 by RC1. 1 by RC1. The third equation, x3 dot equal to minus x1 by x1 alone minus 1 by L 0 0 U of t, coefficient of U of t is 1 by L. That's all. This is the state model. This is A matrix. This is B matrix. What is Y? Y equal to C VC2. That is y equal to x2. That is the equation. If you put them in matrix form, y equal to x1, x2, x3. Here only x1, x2. Therefore 0, 1, 0. Plus the D matrix is 0. That's all. This is output matrix. This is state matrix. This is the first one is state matrix. That is x dot equal to ax plus bu. This is y equal to cx, output equation. That's all. Obtain the state space representation of armature controlled DC motor and the field controlled DC motor. So this is the armature controlled DC motor. Here we can write expression for back EMF equal to EB equal to AB d theta by dt, where theta is the displacement and theta dot is the velocity of this rotor. This is first equation. Second equation is electrical equation. We can write E of t equal to the applied voltage. E of t equal to L dia by dt. Since the current through this is IA, armature current, plus RIA, which opposes the back EMF, opposes the applied voltage. That's why that is also EB of t equal to applied voltage. What are all opposing? The drop in inductance, drop in resistance, and back EMF are opposing the applied voltage. This is second equation. Third equation is mechanical equation. J d square theta by dt square plus B d theta by dt equal to T M. This is third equation, mechanical equation. The relation between the electrical and the mechanical equation is the mechanical torque equal to KT IA. These are the four equations for armature control DC motor. We have to put them in state space model. Let us assume that theta displacement is one state variable x1. Therefore, theta dot equal to x1 dot equal to x2. x1 dot equal to x2 is one state equation. Then theta dot is x2, x1, x2. One more state variable is, let us take IA. IA as third variable, x3. Now, let us substitute all these in these equations and we'll find the final equation. EB equal to KB into d theta by dt is x2. That is x1 dot, that is equal to KB x2. E of t equal to L DIA. IA is x3. IA is x3. Therefore, L DIA by dt is x3 dot plus R x3 plus EB. EB can be written as KB x2. Therefore, x3 dot equal to E of t divided by L minus R by L x3 minus KB by L x2. This is first equation. X3 dot we got. Already x1 dot equal to x2 is first equation. Let us assume this as second equation. We have to find x2 dot. X2 dot can be obtained from this equation. What is that? 3 implies. This is from what? This is 1 implies. This is 2 implies. 3 implies that J x second derivative x2 dot plus B x2 equal to TM. TM equal to KT IA. IA is x3. Or we can write x2 dot equal to KT by J x3 minus B by J x2. So we got 3 equations, 3 first order equations. We have to put them in state space. That's all. If you put them in state space, we'll get the final model. So A is x1 dot, x2 dot and x3 dot equal to 3 by 3 matrix, because there are 3 state variables x1, x2 and x3 plus B matrix multiplied by E of t. E of t is the input. So x1 dot equal to x2 is the A equation. Therefore, 0, 1, 0. x2 dot equal to x2 dot is 0 minus B by J and KT by J. x3 dot equal to what? This is this x3 dot equal to, that is also, there is no x1, that's why 0. And x2 is minus KB by L. Minus KB by L and minus R by L. Minus R by L. The E of t is in the third equation only. No E of t in first equation. No E of t in the second equation. E of t in the third equation. That is 1 by L. That's all. This is the state space model of armature controlled DC motor. Obtain the state space representation of armature controlled DC motor and field controlled DC motor. If it is the field controlled DC motor, this is constant. This is constant. That's why there is no equation for this L and R. IA is constant. Armature. The field produced by this is by EF of t. EF of t. Field produced by this is EF of t. So it has L, F and RF. So the equations are, there is the electrical equation is E field of t equal to L T IF. Current through this is IF. Field current. It is controlled by field. DIF by dt plus RIF. RIF. There is no back EMF here. First equation. Second equation is J d square theta by dt square plus B d theta by dt equal to Tm, as we have seen in the previous. The third equation is Tm equal to Kt IF, not Ia. That is third equation. Only three equations. Now, let us assume that theta equal to x1 equal to, implies that x1 dot equal to theta dot equal to x2. This is the first state equation. We can find for, now replace this by, and we are assuming that theta equal to x1, theta dot equal to x2, two state variable. Third state variable is IF equal to x3. IF equal to x3. That is the third state variable. So now substitute EF of t equal to L dx3 by dt plus bx3 rx3. That is one equation. Therefore, it can be written as EF of t equal to L x3 dot plus rx3 implies x3 dot equal to EF of t divided by L minus R by L x3. This is the first equation. X3 dot we got. Similarly, we can find x2 dot from the second equation. This is first equation implies this. Second equation implies J x2 dot plus bx2 equal to Tm. Tm equal to Kt. IF is x3. That's all. Therefore, x2 dot equal to, this is second and third. Both equation together gives this. X2 dot equal to kt by j x3 minus b by j x2. This is second equation. Already we got one equation. This is the third equation. X1 dot equal to x2. Now we have to put all together. In state space means x1 dot, x2 dot, x3 dot equal to x1, x2, x3 plus E field of t. So x1 equal to x2, therefore 0, 1, 0, only x2, x1 dot equal to x2. x2 dot equal to what we got? Only it is function of x3 and x2, therefore 0 minus b by j kt by j. x3 dot equal to, here we got x3 dot equal to. That is function of x3 alone. Therefore, 0, 0 minus r by L x3. Here, EF of t is in the final equation, only 1 by L, 0, 0. That's all. In no other equation, EF of t. This is mathematical model of field controlled DC motor. Field controlled DC motor. Mathematical model of field controlled DC. The next topic is system realization. In 1960s, there is no microcontroller. 1960s, there is no microcontroller. But United States sent crew to moon. But without doing any simulation, it's not possible to do the practical. We have to check by simulation before doing any practical work. How they did the simulation? All control equations are simulated analog way. Analog simulation. We can simulate analog way by using integrator. We can simulate any differential equation. So if you want to simulate, for example, I'm having a system y of s upon x of s, a transfer function equal to k upon, say, 5 upon 3s plus 1. This has to be simulated by using analog circuits, not digital way. Digital, we know how to simulate. We have to digitize the equation. Then we have to write program. You can use computers to simulate. But analog, how to simulate? That we are going to see now. If you cross multiply this, you will get 3s y of s plus y of s equal to x of s. That is y of s, if you write in time domain, y of t. S y of s means y dot of t. S means derivative. 1 by s means integration. Y dot of t. 3 y dot of t plus y of t equal to x of t. 5x of t. 5x of t. This 5 is there. Therefore, we can write y dot of t differential equation. Y first order differential equation. Y dot of t equal to 5 by 3 x of t minus 1 by 3 y of t. We can simulate this. How to simulate? You know that integrator. If you connect a resistor here and the capacitor in the feedback, it is integrator. It is integrator. If you give any voltage here, that will be integrated and it will be available in the output, but inverted. That is the only difference. So by using integrator, here if you put a sign change here, If you put a sign change, how to put a sign change? Both are R, no gain, only R. If you put like that, integral output in without sign change you will get. Integral output without sign change you will get. So this can be written as symbolically this way. Or you can put integrator sign here. This is integrator. Or you can put this is also equivalent to 1 by S. If you give V in here, integral of V in dt available the output. If you give V in here, the output is integral of V in dt. By using this, we can simulate this in an analog way. I want to simulate this. For that, I am taking this. How we are obtained this? This is from this transfer function we got this. Y dot equal. Let us assume that y of t is available. Let us assume that y of t is available. We can simulate if y of t is available. Take a summing junction. Take a summing junction. Y of t is available. You need 1 by 3 times 1 by 3 times y of t if you take and subtract. X of t is input. X of t is input. 5 by 3 times x of t is given here. These two together, if you add these two together, 5 by 3 times x of t, 1 by 3 times y of t. We are assuming that y of t is available. If you subtract these two, what you will get is y dot of t is available. Y dot of t is available. If you integrate this, what you will get? Y dot of t, if you integrate, you will get y of t. You will get y of t, you will get. So this is analog way of simulation. Analog simulation. Analog simulation of any transfer function. Any transfer function can be converted into this circuit, electrical model. What is the difference between what we have seen in first unit, electrical analogous of mechanical system? We have seen all electrical systems are converted into, all mechanical systems are converted into electrical systems. We did, what is the difference between the two? That is only passive elements. There, only passive elements. Here, active element is there. The integrator is active element. This integrator is active element. So here we are converting this into by using active element. So any transfer function can be simulated analog way. That is very much possible. Now in MATLAB, you can, this 1 by S is available. If you want to simulate in MATLAB, take 1 by S, block is available. Then you can simulate this 5 by S. This is constant block is available. So you can give X of S. You can take feedback and give here. The feedback is multiplied by 1 by 3. You will get Y of T. So this can be simulated in MATLAB also. Analog simulation you can do in MATLAB also. You have to select 1 by S. This is called realization, system realization. We know the transfer function, but how to realize, how to find a physical system for that. That is called system realization. System realization means getting physical system for given transfer function. Getting physical system for a given transfer function. So how to get physical system? There are 4 methods available. One is called controllable canonical realization, observable canonical realization, cascade form realization, and parallel form realization. First, let us see controllable canonical realization. At physical system, there are 4 methods available. One is called controllable canonical realization, observable canonical realization, cascade form realization, and parallel form realization. First, let us see controllable canonical realization. By seeing, directly by seeing one example, we can realize that. Here, one transfer function is given. We have to realize controllable canonical form. What is controllable form? We will see later. Controllable systems, observable systems are there. What is controllable? What is observable? That we will see later in this chapter. One simple sum will be there in controllable. Check whether the system is controllable. Check whether the system is observable. We can observe sun. We can observe moon. Can you control? So these are all examples for observable system. We can observe, that's all. The displacement, how it displays. In a day, it rotates, the earth rotation. In a day, the earth rotates itself one time. 24 hours, it rotates itself one time. It is observable system, not controllable system. Similarly, all physical systems, maybe sometimes it is observable system, sometimes some variables are observable variables, some variables are controllable variables. We have to check whether the system is controllable or not. If it is controllable, then only we can design a controller. Suppose I am controlling, to control the speed of earth means, will it work out? No, because it is observable system. Similarly, if we have any system, we have to check whether it is controllable, observable, or both controllable and observable. Suppose it is controllable, not observable, means it is also difficult. If you observe, then only you can control. If you measure any, observable means measurable. If you measure any variable, then only you can control it. So, all observable variables need not be controllable variables. All controllable variables need not be observable variables. Both may be there, both may not be there. So here we are forming the transfer function can be converted into observable system as well as controllable system. How to convert them into controllable canonical realization? If you realize this way, it will be definitely controllable. Not sure that it is observable. Controllable observable means, suppose it is a second order system, means how many state variables there? X1, X2. If both variables are controllable, then the system is controllable. Suppose X1 is controllable, X2 is not controllable, it means the system is not controllable. It is not completely controllable. You can control X1, but you cannot control X2. If both are controllable, then only it is called controllable system. Similarly, X1 is observable, X2 is not observable, means it is not observable. But both X1 and X2 are observable, then the system is said to be observable system. Here, if you design this way, if you realize this way, realization means finding physical system for given transfer function. If you realize the given system like this, it will be controllable. For that, H of S equal to what? Y of S upon X of S. H of S is transfer function. That is output by input equal to X2, S plus 2 divided by S plus 5. This can also be written as Y of S upon X1 of S multiplied by X1 of S by X of S. I am deliberately writing like that. I am deliberately writing like that is equal to S plus 2 multiplied by 1 by S plus 5. This is equal to this. This is equal to this. This way I am separating. First, let us take X1 of S upon X of S equal to 1 by S plus 5. What you will get? S X1 of S plus 5 X1 of S equal to X of S. Or S X1 of S is X1 dot Multiply by s means derivative. X1 dot of t or simply x1 of t. Simply x1 of t. Hereafter we have what put t in bracket. X1 dot of t plus 5 x1 equal to x of t. X1 dot of t plus 5 x1 of t equal to x. Or it can be written as x1 dot equal to x minus 5 x1. This is one equation. Now take this. Take this. What is this? Y of s upon x1 of s equal to s plus 2. Or y of s equal to s x1 of s plus 2 x1 of s. Or y of t equal to, the output y of t equal to x1 dot plus 2 x1 of t. This is second equation. This is first equation. By using these two, we can simulate. We can find a physical system. First, we have to simulate the first equation. X1 dot equal to x minus 5 x1. Let us assume that x1 is available. X1 is available. As I said earlier, we are assuming that x1 is available. Take 5 times x1. Take 5 times. Amplifier gain is 5. You are getting 5 times x1. 5 x1 available here. It is subtracted. Here, x of s is given, or x is given here. X of t is given here. Or x of s is given here. Here, x1 of s. Both ways you can write. So put an integrator. Here, what you will get? X of t minus 5 x1 of t is x1 dot of t. X1 dot of t. Put an integrator. 1 by s. You will get x1. If you integrate x1 dot, you will get x1. That's all. The first equation is simulated. Physical system for first equation is made. What and all required? One integrator and one summer. If you have one integrator and one summer, you will get one summing junction. That is summer and integrator is there. We can realize the first equation. Second equation, only summer is required. What is that? Y of t. Let us assume that y of t is available. Y of t is available. Y of t equal to what? X1 dot plus, take x1 dot from here and add to get y of t, because y of t equal to x1 dot plus 2 times x1. X1 is available here. Multiply 2 times and give it here. So if you give x of t here, you will get y of t, the output. So this type of realization is called controllable canonical form. Obtain the controllable canonical form for the given transfer function. Obtain the controllable canonical form for the given transfer function. Obtain controllable canonical form of realization means finding physical system. So the first step is h of s can be written as y of s upon x of s equal to y of s upon x1 of s multiplied by x1 of s upon x of s. That is equal to s square plus 2s plus 3 multiplied by 1 upon s power 4 plus 3s cube plus 12s square plus 9s plus 8. This is equal to this. This is equal to this. This is equal to this. Now we have to take the second one. If you cross multiply, what you will get? S power 4 plus 3s cube plus 12s square plus 9s plus 8 multiplied by x1 of s equal to x of s. Or you can say that x1 of s power 4 means fourth derivative. Fourth derivative plus 3 times x1 third derivative plus 12 times second derivative plus 9 times first derivative plus 8 x1 equal to x of t. x1 fourth derivative of x1 of t, third derivative of x1 of t, second derivative, first derivative without any derivative. Let us assume that x1 fourth derivative of x1 of t equal to x of t minus 3 third derivative minus 12 times second derivative minus 9 times first derivative minus 8 times x1. This is how it can be simulated. Let us assume that x1 is available. Let us assume that x1 of t is available. x1 of t is available. If we assume x1 of t is available, we are going to give x of t as input because it is plus sign. And this is, let us assume that we are assuming that x1 fourth derivative is available. x1 fourth derivative is available. If you integrate once, what you will get? If you integrate once, you will get here, what you are getting is x1 3 dot. x1 fourth dot is integrated means x1 3 dot you will get. Once again, if you integrate, what you will get? x1 double dot you will get. Once again, if you integrate, you will get here x1 dot you will get. If you integrate one more times, you will get x1 of t. We are assuming that x1 of t is available. If you integrate x1 to the fourth derivative is integrated, you will get the third derivative. Once again integrated, you will get the second derivative. If you integrate first derivative, you will get x. So 4 integrators are in cascaded form. 4 integrators are in cascaded form. Now, x1 to the power 4, fourth derivative is available. We are assuming that this is available. But this is equal to what? X of t. That is given here. What are the remaining things we have to give? These are the 4 elements that we have to give. Third derivative is available here. Third derivative is available here. How many times we have to multiply? 3 times we have to multiply. And we have to subtract from this. So we got this and this we got now. This and this we got subtracted. Now 12 times second derivative we have to subtract. 12 times second derivative. So 12. That is also subtracted from the summing block. 9. This is also over. Now 9 times first derivative. Take this, multiply by 9 and subtract. Then take 8 times of x1. That is also has to be subtracted. So all are subtracted from the summing junction. You got x1 of t. Now x1 of t is available. Now take the first equation. What is that? Y of s upon x1 of s is the first equation. That is equal to s square plus 2s plus 3. Cross multiply y of s equal to what? Y of s equal to s square x1 of s plus 2s x1 of s plus 3 x1 of s. S square means second derivative, x1 double dot plus 2 times s means first derivative, x1 of t plus 3 times x1. So take double derivative. Double derivative is available here. Add together to get y of s. Double derivative 2 times single derivative. Sorry, this is third derivative. Double derivative is taken here. Single derivative. How many times we have to multiply? Single derivative 2 times. Multiply by 2, add with this. Add here. 3 times x1. 3 times x1. 2 times x1 dot. 1 time x double dot and x1. If you add all together, you will get y of t. This is output. This is input. So what is required to design this system? 4 integrators. That's all. If you have 4 integrators and 2 summing blocks, if you have, you can design this transfer function. 4th order system you can design. This is in controllable canonical form. Controllable canonical form. We have seen how to obtain controllable canonical form of realization. After realization, we can obtain controllable canonical form of state model also we can get from this realization. That we will see now. From this we can get controllable state model. Now from this we can get controllable state model. So first we got from transfer function, we got controllable canonical realization. That is physical model. From that physical model, we can get a state model which is controllable. Controllable state model. To obtain that, this is x1. Therefore, here it is x1 dot. This is x1 means this is x1 dot. Therefore, x1 dot equal to what? x2. This is x2. Therefore, before integration, it is x2 dot. This is x2 dot means what? This is x3. x3 means before that it must be x3 dot. x3 dot equal to what? x3 dot equal to x4. Before x4, what will be there? x4 dot will be there. That's all. Now we can write the equation. Here we can put equal to x1 dot equal to x2, x2 dot equal to x3, x3 dot equal to x4, x4 dot equal to sum of all these things. So we can write the equation x1 dot equal to x2, x2 dot equal to x3, x3 dot equal to x4, and x4 dot equal to what? Sum of all these things. That is x of t minus 3 times here you notice that 3 times minus 3 times x4 minus 3 times x4 minus 12 times x3 minus 12 times x3 minus 9 times x2 minus 8 times x1 that is x4 dot. So we can put this in matrix form as x1 dot, x2 dot, x3 dot, and x4 dot equal to, this is a state matrix, A matrix. Here you will have x1, x2, x3, x4 plus this is B matrix multiplied by x of t is the input. Now what is the x1 dot equal to x2? Therefore we can write 0, 1, 0, 0. x2 dot equal to x3. Therefore 0, 0, 1, 0. x3 dot equal to x4. 0, 0, 0, 1. And x4 dot equal to minus 8 times x1 minus 9 times x2 minus 12 times x3 minus 3 times x4. And this has x of t, let's say 1. All other no x of t, therefore 0. That's all. This is A matrix, and this is A matrix, this is A matrix, and this is B matrix. That's all. This is controllable state model. Controllable state model. That's all. Sometimes and the examiner may ask you to find the controllable state model instead of realization. In that, you have to physically realize first, then you have to name like this. How to name that? The final output is x1. So before the integration, it must be x1 dot. This is x1 dot means it is equal to x2. Before x2, it must be x2 dot. This x2 dot must be equal to x3. Before integration, x3 must be x3 dot. That is equal to x4. Before x4, it must be x4 dot. That's all. But x4 dot is sum of all these things. That's why we got this equation. Notice that in controllable canonical form, the last row, A matrix has last row all elements, and all other rows it has off diagonal elements. These are all called off diagonal elements. So if this is in this pattern, then it is in controllable canonical form. A matrix is in this pattern, it is controllable canonical form.
Observable canonical realization. Given that h of s equal to s square plus 2s plus 3 upon 4 s power 4 plus 3s cube plus 12s square plus 9s plus 8. Fourth order system. So this is equal to what? Y of s upon u of s. If you cross multiply, you will get s power 4 plus 3s cube plus 12s square plus 9s plus 8 multiplied by y of s equal to s square plus 2s plus 3 u of s. If we keep this s power 4 y of s on the left hand side and keep other things on the right hand side, what we will get is minus 3s cube y of s plus s square x of s minus 12s square y of s plus 2s u of s. This is u of s. We assume input is u of s. 2s u of s minus 9s y of s. Finally, 3 u of s minus 8 y of s. We know that u of s is input, y of s is output. Y of s, therefore, y of s equal to, bring this s power 4 to the right hand side, you will get 1 by s minus 3 times y of s plus s square divided by s power 4 is 1 by s square u of s minus 12 y of s. Plus divide by s power 4. This term you will get 1 by s cube 2 u of s minus 9 y of s plus 1 by s power 4 3 u of s minus 8 y of s. That's all. Now we can directly realize this expression. Here number of integrators equal to 1. Here number of integrators 2. Number of integrators 3. Number of integrators 4. That's all. Let us assume that y of s is available. Y of s is available. Similarly, let us assume that u of s input is available. One by s. Yes. Now another link. We are going to draw the signal flow graph. So another link with unity gain, and we are going to add one more 1 by s. Again, a unity link, and we are going to add one more integrator. Another unity link, one more integrator. 1 by s. How many integrators? 1, 2, 3, 4 integrators we include. Now we have connected with this. Now take the last term. How many integrator? 4 integrators. 1, 2, 3, 4 integrators. So we have to take a feedback of 8 minus 8 minus 8. Here is 3 times. 3 times u of s minus 8 times y of s. That is equal to x1 dot. Therefore, this is x1. This is x1. Now, second term, if you consider 9 y of s, you have to take 9 y of s. It should be given here 9 y of s minus 9 y of s. And how many x of s? 2 u of s. 2 u of s. 2 u of s. If you add these two together, then it is called x2 dot. x2 dot. Here you will get x2. Because of that integrator, you will get x2 here. The third one is 12 y of s with the 2 integrator. 12 y of s. So minus 12. And how many u of s? 1 u of s. 1 u of s. 1 u of s. Signal flow. 2 integrators. This loop has 2 integrators with gain 12. This forward part has 2 integrators with gain unity. Third one is only y minus 3 times. That's all. Minus 3 times. That's all. Over. Now we have to obtain the here x2. Therefore, this is x3 dot. Therefore, this is x3. This is x4 dot. That's why this is x4. Now we can obtain the state observable state model. Observable state model we can get from this physical model. This is the physical model with how many integrators? 4 integrators. We have drawn in terms of signal flow graph instead of block diagram. Here you can write expression for this x1 dot. Therefore, we can write x1 dot equal to what are the inputs to this node? Minus 8 times y of s and 3 times u of s. 3 times u of s and minus 8 times y of s. This is equal to 3 times u of s minus 8 times y of s. Y of s equal to what? X4 is one time multiplied and given as input. Y node is only one input, that is x4. Therefore, y equal to x4. Therefore, we can write minus 8 times x4. This is first equation. Second equation, from here we can write, that is x2 dot equal to how many x1? 1 x1 plus 2 times u of s, 2 times u of s, 1 x1 and minus 9 times y of s, 9 times y of s. That is equal to 2 u of s plus x1 minus minus 9 x4, because y of s equal to x4. Here we are mixing the frequency domain and time domain. But in fact, we should not mix frequency domain and time domain. But here, interchangingly, we are using both frequency domain and time domain. But better to write in time domain. X3 dot equal to, this is x3 dot. X3 dot equal to x2 plus u of t minus 12 y, that is equal to x2 u of t plus x2 minus 12 y, that is x. This is third equation. The fourth one is x4 dot, that x4 dot equal to what? X4 dot equal to only two inputs. One is x3, another one is 3 times y, that is equal to x3 minus 3 x4. This is fourth equation. Now we can put all these together and we can write the state model. That is x1 dot, x2 dot, x3 dot, x4 dot equal to x1, x2, x3, x4 plus u of t. X1 dot equal to 3 u of s minus 8 x4. All others are 0. Second equation, 2 u of s and x1 is 1, x4 is minus 9. All others are 0. Third equation, 1 u of s and x2 is 1 and x4 is minus 12. All others are 0. And the final equation, x3 is 1 and x4 is minus 3. All others are 0. That's all. This is A matrix. This is A matrix. This is here no u. That's why here 0. 0. This is B matrix. This is B matrix. What is the output equation? Y equal to x4. That That's all. Therefore, y equal to what is that? 0, 0, 0, 1, x1, x2, x3, x4. That's all. D matrix is 0. This is the observable state model. This is observable state space model. This is what? This is observable physical realization or observable realization, hardware model. This is one integrator, two integrator, third integrator, and fourth integrator. Four integrators and summing blocks form this circuit. The same observable canonical form can be realized by using Mason's gain formula. Y of s upon u of s equal to s square plus 2s plus 3 upon s power 4 s power 4 3 12 s square plus 9s plus 8. This is the given transfer function. For that, we have to form the observable canonical form. We have to convert this like Mason's gain formula. Divide the numerator and denominator by s power 4. What you will get is 1 by s square plus 2 by s cube plus 3 by s power 4 whole divided by 1 plus 3 by s plus 12 by s square plus 9 by s cube plus 8 by s power 4. Here, this can also be written as 1 by s square plus 3 by s cube plus 2 by s cube, 3 by s power 4 whole divided by 1 minus 3 by s minus 12 by s square minus 9 by s cube plus 8 by s power 4. This is identical to Mason's gain formula. What is Mason's gain formula? T of s equal to 1 by delta pk delta k. Number of forward paths. So first forward path, second forward path, third forward. The denominator delta is in the denominator. This is first loop, second loop, third loop, fourth loop. So immediately we can draw the signal flow graph. We have to combine s square and s square, and we have to combine s cube and s cube. We have to combine s power 4 and s power 4. No s term, 1 by s term in the numerator. Then you will get the signal flow graph. What is available? The available is y of s. Y is available. What is input? U is the input. So first let us finish the forward paths. How many integrators? 4 integrators. This is 1. This is 1 by s. 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 1, 2, 3, 4. This is u. One forward has 4 integrators. Therefore, its gain is 3. Therefore, the gain of this forward path with 3 gain. How many integrators? 1, 2, 3, 4 integrators. So this is over. Next one is 3 integrators with the gain 2. 3 integrators. So here it will join. How many integrators? 3 integrators with gain 2. Third one is 1, 2 integrators. So here it will come here. So you can give 1 by s square. This is 1 by this forward path is 1 by s square, 2 by s cube, 3 by s square. All forward paths are over. Now we have to draw the loop gains. Let us start with the 8. 8, that loop gain is 8 times s power 4. All will be included and the gain is 8. Minus 8. Minus. Then 3 integrators gain minus 9. Next one is 2 integrators with gain 12. 2 integrators with gain 12. And 1 integrator with gain 3. 1 integrator with gain 3. Minus 3. That's all. Loops are over. So this is the final signal flow graph. From this we can write the state model, observable state model. This is observable realization. This is observable realization. Now let us find the observable state model. The observable state model, we have to assume that this is x1 dot. This is x1 dot. This node is x1 dot. This node is x2 dot. This node is x3 dot. This node is x4 dot. Therefore, x1 dot equal to, therefore, x1 dot equal to minus 8 times y plus 3 times u. This is x4 dot means after integrator it is x4. x3 dot means after integrator this is x3. x2 dot means after integrator it is x2. x1 dot means after integration it is x2. So the input to y is only x4. Therefore, this y can be replaced by x4. Therefore, minus 8 x4 plus u. What is x2 dot? x2 dot equal to this. Consider this this junction x2 dot. What are the inputs? 3 inputs. What are the x1 minus 9y, y can be written as x4 and plus 2u. This is second equation. This is first equation. then x3 dot equal to x3 dot equal to this junction. You have to consider this junction. How many inputs? 3 inputs. What are they? One is x2, another one is minus 12 y, that is x4, then 1 xu. That's all. This is third equation. What is x4 dot? X4 dot is how many inputs? Only 2 inputs. Therefore, that is equal to x3, one input. This is the junction. Another input is minus 3y, minus 3x4. Therefore, now we can write in state model x1 dot, x2 dot, x3 dot, and x4 dot. That is equal to x1, x2, x3, x4 plus this is B matrix multiplied by E. Now 8x4, minus 8x4, that's a minus 8x4, and U equal to 3. All others are 0. x2 dot equal to 8x4, sorry, x2 dot equal to minus 9x4 and 1x1 and 2u, all others are 0. x3 dot equal to 0, 1, no x3 and minus 12, u is 1. x4 dot is only x3 and x4, that is minus 3. There is no u, that's all. We got the state model. What is output equation? Y equal to x4, that's all. Therefore, we can write y equal to 0, 0, 0, 1 multiplied by x1, x2, x3, x4. That's all. This is the observable state model.
This is the given transfer function y of s upon u of s. This is the given transfer function. For that, we have to obtain the cascade form realization. In cascade form realization, we have to separate this into so many transfer functions in cascade. That's why we have to factorize further. If you factorize that, what you will get s plus 1, s plus 2 upon s plus 5, s plus 3 and s plus 0.5. So this way we further factorized this. This can be written as cascade of 3 transfer function s plus 5, s plus 1 upon s plus 3, s plus 2 upon s plus 0.5. We have to realize these 3 transfer functions separately, and we have to cascade. So we have to realize each in controllable canonical form. Controllable canonical form. For that, let us consider each one can be named as H1, H2, H3. H1 of S, H2 of S multiplied by H3 of S. Let H1 of S be Y1 of S upon U of S. The input is taken as input and the new output is Y1. So this Y1 will be input to the next state, next block. That's why Y1 of S, its output is Y2 of S. Next block is y2 is the input and output is y of s. So if you cancel y1 and y2, you'll get y of s upon u of s. Now consider the first, and we have to consider y1 of s upon u of s. That is equal to 5 upon s plus 5. That is equal to for controllable canonical form, we will assume that y1 of s upon x1 of s multiplied by x1 of s upon u of s, where y1 of s is upon x1 of s is assumed as 5, and x1 of s by u of s is assumed as 1 by s plus 5. So now if you cross multiply x1 of s, this is assumed like this and this. Then x1 of s upon u of s equal to 5 upon 1 upon s plus 5. If you cross multiply, you will get this implies s plus 5 x1 of s equal to u of s. So this can be written as x1 dot plus 5x1 equal to u of t, or x1 dot equal to u of t minus 5x1. This is one equation. What is the next part is y1 of s upon x1 of s, that is equal to 5. Therefore y1 of s equal to 5x1 or 5x1 of s. That is y1 equal to 5x1. This is another equation. So we can obtain the controllable canonical form for this. Let us assume that x1 is available. So we subtract 5 times x1, and if you add u of t together, you will get x1 dot. If you integrate this x1 dot, you will get x1. Now we have to get y1. y1 is 5 times y1 is, this is x1. You multiply this by 5 times, you will get y1. So this is one part is over. The first part is over. Now consider the second part. S plus 1 upon s plus 3. That is equal to what we assumed, y2 of divided by y1 of s. Therefore, y2 of s upon y1 of s, that is equal to y2 of s upon x2 of s multiplied by x2 of s upon y1 of s, equal to s plus 1, and this is 1 by s plus 3. Now consider x2 of s upon y1 of s equal to 1 by s plus 3. This implies S x2 of S plus 3 x2 of S equal to y1. Or x2 dot equal to y1 minus 3x2. This is one equation. X2 dot equal. If you write for y, if you consider the second part s plus this, what you will get is y2 of s upon x2 of s equal to s plus 1. Therefore, what you will get is y2 of s equal to sx2 plus x2. y2 equal to x2 dot plus x2. The equation is x2 dot equal to y1 minus 3x2 and another equation is y2 equal to x2 dot plus x2. Assume that x2 is available. x2 is available. Take 3 times x2, add this is y1 minus 3, y1 minus 3x2 is x2 dot. If you integrate this, you will get x2. Now y2 equal to what? x2 plus x2 dot. That is y2. So second equation also over. Now we have to consider the third equation. That is y of s upon y2 of s. That is equal to y of s upon y2 of s. S plus 2 will be s plus 0.5. S plus 2 upon s plus 0.5. So that is equal to y of s upon x3 of s multiplied by x3 of s upon y2 of s. So consider x3 of s upon y2 of s equal to 1 by s plus 0.5. This is equal to s plus 2 multiplied by 1 by s plus 0.5. If you cross multiply, you will get, I'm writing directly, x3 dot equal to y2 minus 0.5 x3. We got one equation. Consider the second part. Consider the second part. What is that second part? Y of s upon y2 of s equal to s plus 2. Sorry. Y of s upon x3 of s equal to s plus 2, or y of s equal to s x3 of s plus 2 x3 of s. That is equal to y of t equal to x3 dot plus 2 x3. This is another equation. x3 dot. If you combine these two together, you will get the third equation. What is the third equation? Third realization. That is x3 dot. x3 is available. x3 is available. Take x3, multiply 0.5 times. Multiply 0.5 times. You will get x3 dot. x3 dot. If you integrate this, you will get x3. So what is y? Y is sum of 2x3 and sum of x3 dot. x3 dot. That is y That's all. If you cascade all these three together, you will get cascade form of realization. Cascade form of realization. Cascade form of realization. So we combine all the diagram together so that you will get here, this is u of t plus 5 times this is x1 dot 1 by s. This is x1. Then y1 equal to 5 times x1 is y1. 5 times x1 equal to y1. Now combine this second you have to combine. Y1 is the input, y2 is the output. So if you combine this, you can directly connect this y1 here, and you have to subtract 3 times x2. If you integrate x2 dot, here x2 dot, here x2. What is y2? Y2 is sum of x2 and x2 dot. That is y2. Now you got y2. Here y2 is the input and y is the output. So you connect here. Y2 is, that is x3 dot. You put 1 by s, you will get x3. Here we have to multiply 0.5 times 2 times y, 2 times x3, and 1 times x3 dot. If you multiply, you will get y. This is realization of h1. This part is realization of h2. This part is realization of h3. This is x1 dot. This is x1 dot. This is x2 dot. This is x3 dot. This is y. So we have to write expression for x1 dot, x2 dot, and x2 dot, x3 dot, and y. Let us write x1 dot. X1 dot equal to 5x1 minus, this is minus u of t minus 5x1. 5x1. x1 and x2 dot equal to what? X2 dot equal to y1 minus 3x2. x3 dot equal to what? x3 dot equal to y2 minus 0.5 x3. But in state equation, y and y2 should not be there. That's why let us write y1 equal to what? 5 times x1. Therefore, 5x1 minus 3x2. This is also equal to y2 equal to what? Y2 equal to consists of two components. One is x2 and x2 dot. 5 times y2 is y2 equal to, here this y2 equal to x2 plus x2 dot. Therefore, instead of y2 we can write x2 plus x2 dot minus 3 minus 0.5 x3. x2 dot equal to what? x2 dot equal to, already in the previous equation we got, that is 5x1 minus 3x2 minus 0.5 x3. That is equal to, if you group x2 together, you will get minus 2x2 minus 0.5 x3. So we got x3 dot. x3 dot. This is second equation. x2 dot. This is first equation. Now we have to write expression for y. Y equal to what? Y equal to 2x3 plus x3 dot. That is equal to 2x3 plus x3 dot equal to 5x1 minus 2x2 minus 0.5 x3. If you combine x3 together, you will get 5x1 minus 2x2 minus 1.5 x3. If you put them in matrix form, you will get x1 dot, x2 dot, x3 dot equal to x1 dot equal to 1 u of t 5x1 minus 5x1. That's all. All other two are 0. x2 dot equal to 5x1 minus 3x2 0. No u. Next one is 5x1 minus 2x2 minus 0.5 x3. Notice that these off diagonal elements are 0 in this form. And here also u equal to 0. This is A matrix and this is B matrix. That is x dot equal to ax plus b u. We got. What is y? Y matrix equal to 5 minus 2, 1.5 multiplied by x1, x2, x3. D matrix is 0. D matrix is 0. Q of t. No need to write this. That's all. This is state model of cascade form. Notice that off diagonal elements are upper off diagonal elements of A matrix is 0. That is also having some advantage. As far as interaction is concerned, you will get less interaction than a complete non-zero A matrix. We'll compare with cascade realization. That's all about cascade realization. Parallel form realization. For that, we have to do the, for this we have to do the partial fraction. How many factors in the denominator? 3 factors. Therefore, we can factorize into 3 transfer functions. A upon s plus 1 plus b upon s plus 3 plus c upon s plus 4. Then we have to realize each by using controllable canonical form. Then we have to connect all outputs together. This can be assumed as y1 of s upon u of s. This is y of s upon u of s. This can be assumed as y2 of s upon u of s plus y3 of s upon u of s. Like that we have to assume. Now we have to find a, b, c. A equal to what? A equal to s into s plus 2 upon s plus 1 multiplied by s plus 3 multiplied by s plus 4 multiplied by s plus 1. S equal to minus 1. If you substitute s equal to minus 1, a is minus 1 plus 2 upon minus 1 plus 3 and the minus 1 plus 4. That is equal to minus 1 multiplied by 1 upon 2, 3. That is minus 1 by 6. B equal to multiply s multiplied by s plus 2 upon s plus 1 multiplied by s plus 3 multiplied by s plus 4, s plus 3 getting cancelled, and s equal to minus 3. We substitute minus 3 plus 2 minus 1 upon minus 3 plus 1 minus 2 minus 3 plus 4 plus 1. That is equal to 3 minus, therefore minus 3 by 2. 3 by 2. Then we have to find C. C equal to s multiplied by s plus 2 upon s plus 1, s plus 3, s plus 4 multiplied by s plus 4, where s equal to minus 4. That is equal to minus 4. Minus 4 plus 2 is minus 2 upon minus 4 plus 1 minus 3 minus 4 plus 3 minus 1. 4 minus, therefore plus 8 by 3. 8 by 3. Therefore, the given transfer function becomes instead of a minus 1 by 6. Instead of b minus 3 by 2. Instead of c, you have to consider 8 by 3. If you realize first case, what you will get is you'll take here 1, 3, 4. y1 of s upon u of s, y2 of s upon u of s, y3 of s upon u of s. That is equal to minus 1 by 6 s plus 1, s plus 3 minus 3 by 2, s plus 4, 3, 8 by 3. y1 of s upon x1 of s multiplied by x1 of s upon u of s. That is equal to minus 1 by 6 multiplied by 1 by s plus 1. This implies x1 by x1 of s by u of s equal to 1 by s plus 1. Therefore, this implies x1 dot equal to u minus x1. U minus x1. This is one equation. And minus 1 by 6 y1 of s upon x1 of s equal to minus 1 by 6. Therefore, y1 equal to minus 1 by 6 x1. This is another equation. Similarly, this second equation is implies y2 of s by x2 of s, x2 of s upon u of s, that is equal to minus 3 by 2 multiplied by 1 by s plus 3. This implies 1 by s plus 3 means you have to group this and this. You will get x2 dot equal to u minus 3x2. By looking, we can write. Here, you will get y2 equal to, you combine this and this. Combine this and this, you will get y2 equal to minus 3 by 2 x2. This is another equation. In the same way, if we equate this y3 of s upon x3 of s, x3 of s upon u of s, that is equal to 8 by 3 multiplied by 1 by s plus 4. You have to combine this and this together, this and this together. If you combine, what you will get, x3 dot equal to u minus 4x3. This is one equation. Another equation is y3 equal to 8 by 3 x3. This is another equation. Now we have to realize all in parallel. The first equation is what? The first equation is here. First equation is here. Second equation is this. This is the third equation. First one is u is the input and 1 by s, x1 is available, minus x1, u minus x1 equal to x1 dot. If you integrate that, you will get x1, y equal to, y1 equal to minus 1 by 6 times. This is y1. What is second equation? Second equation also, the input is u. Second equation, x2 dot u minus 3 times x2 equal to x2 dot. If you integrate this, you will get x2. This has to be subtracted 3 times x2. y2 equal to minus 3 by 2 times x2 is y2. y2 also we got. Here also u is the input. The third equation is again u is the input. That is x3 dot if you put 1 by s, you will get x3. x3 has to be multiplied by 8 by 3 times. That is y3. So x3 has to be multiplied 4 times and subtract, you will get x3 dot. x3 dot equal to u minus 4 times x3. So all are u, so we can combine all together and here you can give u of t as the input. All y's, if you add it together, you will get y. You will get y of t. That's all about parallel form of realization. Now we have to get state model. Already we got that is x1 dot, x2 dot, x3 dot equal to what is x1 dot equal to -1, all other things are 0. x2 dot equal to -3, all others are 0. x3 dot equal to -4. A diagonal matrix x1, x2, x3 plus B matrix is what? Here 1 time u, x1 dot also 1 time u, x3 dot also 1 time u. So u of t. This is B matrix, this is A matrix. What is y? Y equal to y1 plus y2 plus y3. That is equal to y1 equal to minus 1 by 6 x1 minus 3 by 2 x2 minus 8 by 3 x3. This can be written in the matrix form like this. Equal to minus 1 by 6 minus 3 by 2 minus 8 by 3 multiplied by x1, x2, x3. That's all. This is output equation. This is output equation. This is state equation. This is state equation. That's all about the parallel form of realization. Important. Already we have seen the parallel form of realization. We have seen the parallel form of realization. If you see the A matrix, the previous example that you can see, the A matrix is a diagonal matrix. Because of diagonal matrix, two advantages. One is there is no interaction among the state variables. That is another advantage is each first order equation, first order differential equation can be solved independently. It means x1, x2, etc., xn are independent variables. If A matrix is a diagonal matrix, that is the advantage of having diagonal matrix. How to convert the state model, which is not diagonal, which is not having the diagonal matrix, how to convert that into a diagonal matrix that we are going to see today. Diagonalization. That is called, what is state model? X dot equal to ax plus bu and y equal to cx plus du. If A matrix is not diagonal, then there is interaction among x variables, and each state first order equation is not independent. If A is diagonal matrix, then x1, x2, etc., xn becomes independent. That is the advantage. That's why how to convert this equation into a diagonal matrix that we are going to see. Let us assume that X equal to PZ. If you write in terms of Z transformed variable Z dot, then it becomes diagonal. Let us transform X into PZ, where Z dot equal to A cap X plus B A cap Z dot equal to A cap Z plus BU and Y equal to B cap U. C cap Z plus D cap U. If you convert this X dot into Z dot, then the A cap will be a diagonal matrix. X dot equal to what? This equation 1 becomes 1 implies using equation 2, 1 becomes X dot equal to P Z dot equal to A P Z plus BU. Pre-multiply on both sides by P inverse, because P is a matrix. P inverse P Z dot equal to P inverse AP Z plus P inverse BU, or P inverse P Z dot. This is equal to I Z dot equal to P inverse AP Z plus P inverse BU, or Z dot equal to P inverse AP Z plus P inverse BU. This can be called as A cap. This can be called as B cap. Therefore, Z dot equal to A cap Z plus B cap U. B cap U, where Z cap is a diagonal matrix. Where Z cap is A cap is a diagonal matrix. The output equation Y equal to Cx plus Du. X equal to Pz, therefore Cpz plus Du. This is equal to Cp equal to what? C cap Z plus D cap U, that is Y. Therefore, this X dot equal to Ax plus Bu is transformed into Z dot equal to A cap Z plus BU and Y equal to C cap Z plus DU. This is a diagonal matrix. This is here, A cap is diagonal matrix. How to find P? We have to find P. The P is called the model matrix. P is called model matrix. How to find the P, that we'll see. So we'll find P after finding the eigen values and eigenvalues are roots of characteristic polynomial are called eigenvalues. First, we have to find the characteristic polynomial. What is X dot equal to Ax plus Bu is the state variable, and Y equal to Cx plus Du. If we take Laplace transform, what you will get? S X of S minus X of 0 equal to A X of S plus B U of S, that you will get. So it can also be written as S X of S minus A X of S equal to X of 0 plus B U of S. or it can be written as Si minus A, Si minus A, x of S equal to x of 0 plus B u of S. Multiply on both sides by x, Si minus A inverse, you will get x of S equal to Si minus A inverse x of 0 plus Si minus A inverse B u of S. It means what? This is differential equation, x dot. We took Laplace transform. Finally, we find x. If we take inverse Laplace, you will get x of t. You will get x of t. So we can solve the differential equation by multiplying on both sides by Si minus A inverse. If you find Si minus A inverse, we can find the solution. We can find the solution. That is one important point. If you assume this is 0, null matrix, if x of 0 is a null matrix, then x of S equal to Si minus A inverse B u of S. Si minus A B u of S you will get. If you substitute this in Y matrix, what you will get? Y of S equal to C x of S plus D u of S. You substitute this x of S assuming this null matrix. Therefore, what you will get is C x of S equal to what? Si minus A inverse B u of S plus D u of S. It is equal to what? Y of S. It is equal to Y of S. Therefore, the transfer function T of S equal to transfer function T of S equal to what? Y of S upon U of S. Y of S upon U of S. If you bring this to Y of S to the left hand side, you will get C Si minus A inverse B u of S, sorry, B plus D. We have to find C Si minus A inverse B plus D, that is transfer function. So once you write like this, instead of writing like this, we can write like this. Si minus A can be written as adjoint matrix of Si minus A divided by determinant of Si minus A plus D. If we take LCM, Si minus A is the denominator. In a transfer function, denominator is the characteristic polynomial. Therefore, determinant of Si minus A equal to 0 is the characteristic polynomial. Si minus A is the characteristic polynomial. The determinant of Si minus A. Why this is the roots of characteristic polynomial are called eigenvalues. Eigenvalues. Let them be. Suppose if it is nth order system, means how many eigenvalues you will get? Lambda 1, lambda 2, lambda 3, etc. Lambda n. Eigenvector. Lambda i's are called eigenvalues. then it will satisfy lambda I minus A into xi equal to 0. Yeah, non-zero solution xi to the above equation is are called eigenvectors. A non-zero solution xi to the above equation is called eigenvector. How to find xi? Xi equal to pre-multiply on both sides by lambda I minus A inverse. You will get lambda I A minus A inverse multiplied by 0. This can be written as adjoint matrix of lambda I minus A. Lambda I means eigenvalue. For each eigenvalue, you can write one such equation. For inverse, we are writing the definition divided by determinant of lambda I minus A multiplied by 0. This xi, when it will exist, it is 0 because it is multiplied by 0. When xi will get a non-zero solution, if you get the undefined value of this, if it is 0 by 0, is undefined. So if you make this is equal to 0, if you make this is equal to 0, then you will get a xi value. It is what? This is nothing but characteristic equation. And substitute the roots of that characteristic value. Therefore, you will get a value xi if lambda I minus A is 0. So you can get set of xi values. The set of xi values are called model matrix. Model matrix P is set of these values x11, x12, x21, x22. Like that you will get. This is the model matrix for a second order system. Model matrix for second order system. x11, x12, x21, x22 are values of xi when lambda I minus A is equal to 0. If it is not equal to 0, if this is not equal to 0 means xi equal to 0. But a non-zero solution is required means you have to force lambda I minus determinant of lambda I minus A to 0. That's all. So the solution of this xi's are called, that is eigenvectors forms a model matrix P. If you know P, you can diagonalize the matrix A. By an example, we'll find the eigenvalues and eigenvectors. We'll find the eigenvalues and eigenvector. Consider the system x dot equal to ax plus bu and y, the output equation y equal to cx plus du, where a equal to 3, a equal to minus 3, 1, 1, minus 3, b equal to 1, 0, c equal to 1, 0, d equal to a 0 matrix. This is given. The first step is find the eigenvalues and eigenvectors. Second point is diagonalize the A matrix. We can put hence diagonalize the A matrix. This is the two parts of this question. First, let us find the eigenvalues and eigenvectors. To find eigenvalues, we have to find Si minus A equal to 0. Determinant of Si minus A equal to 0. Si is what? S 0, 0 S is Si minus A. A equal to minus 3, 1, 1, minus 3 equal to 0, or S plus 3 minus 1 minus 1 S plus 3 equal to 0. Determinant of this is equal to 0. What is the determinant? Determinant of this is S plus 3 whole square minus 1 equal to 0, or S square plus 2 6S plus 9 minus 1 equal to 0, or S square plus 6S plus 8 equal to 0. The roots of them are minus 2, comma, minus 4. Minus 2, comma, minus 4. Therefore, eigenvalues are minus 2, comma, 4, minus 4. That's all. Now let us find the eigenvectors. Eigenvectors are solution of this, that is lambda I minus A xi equal to 0. Solution of this is so lambda I means the first value is minus 2. Therefore, minus 2, 0, 0 minus 2 is lambda I. Lambda I minus A. A is what? A is minus 3, 1, 1, minus 3 multiplied by xi. Here x1, x2 equal to 0. That is equal to minus 2 plus 3. Minus 2 plus 3 is 1. This is minus 1. This is also minus 1. Minus 2 plus 3 plus 1. So we got x1, x2 equal to 0. So what is the equations? If you multiply, what you will get is x1 minus x2 equal to 0. Here, minus x1 plus x2 equal to 0. So if you find this is, you might have studied in algebra, linear algebra, that if determinant of AD is less than the rank of AD is less than n, means you will get infinite number of solutions. Here also infinite number of solutions. That's why we have to assume x1 equal to 1 means x2 equal to also 1. That's all. Therefore, the eigenvector for lambda equal to minus 2 is 1, 1. That's all. One vector we got. Similarly, we have to find another vector, that is lambda I minus A multiplied by xi equal to 0. Here, lambda I is minus 4. Therefore, minus 4, 0, 0 minus 4 minus A. A is minus 3, 1, 1 minus 3. Xi, that is x1, x2 equal to 0. Minus 4 plus 3 is minus 1. 0 minus 1 is minus 1. 0 minus 1 is minus 1. Minus 4 plus 3 is minus 1. Multiplied by x1, x2 equal to 0. Or you will get the equation of x1 minus x2 equal to 0. Take first row, first column. You will get another equation, same equation, x1 minus x2 equal to 0. It means you will get infinite number of solutions. Let's assume that x1 equal to 1, therefore x2 equal to minus 1. Therefore, the another vector x1, x2, another eigenvector is 1 minus 1. Therefore, P matrix is equal to, combine these two eigenvalues. P matrix is 1, 1, 1 minus 1. This is the P matrix. So this is the eigenvectors. Eigenvectors are, this is eigenvectors. Eigenvectors. 1, 1, 1 minus 1 is the eigenvectors. If you combine eigenvectors, you will get the P matrix. Now we can diagonalize by using P matrix. What is diagonal matrix? A cap equal to P inverse AP. So P matrix equal to what? P matrix equal to 1, 1, 1 minus 1. Therefore, P inverse. Since it is a 2 by 2 matrix, we can apply thumb rule to find the inverse. We have to interchange these two. So minus 1, 1. Interchange the diagonal elements and negate the off diagonal elements. Therefore, minus 1, minus 1. That is P inverse. Otherwise, you have to find the adjoint matrix and determinant of matrix P. So P inverse you got. Therefore, we can find the P inverse AP. P inverse is 1, minus 1, minus 1, 1. A is minus 3, 1, 1, minus 3. And P matrix is 1, 1, 1, minus 1. So if you multiply these two together, what you will get? We have to write as such 1, minus 1, minus 1, 1. If you multiply this first row, first column, minus 3 plus 1, minus 2. Minus 3 plus 1, minus 2. First row, second column, minus 3, minus 1, minus 4. Second row, first column, 1, minus 3, minus 2. Second row, second column, 1, plus 3, plus 4. So if you multiply again, first row, first column, you will get minus 2, plus 2, plus 2, 4 you will get. First row, second column, this is plus 4, minus 4, that's why 0. Again, second row, first column, you will get, this becomes positive, this becomes negative, that's why again 0. Second row, second column, plus 4, plus 4, 8. The determinant, we have to divide this by determinant of P. 1 by determinant of P. Determinant of P equal to what? This is minus 1, minus 1, that is minus 2. Therefore, P inverse is minus 1 by 2. Minus 1 by 2. Minus 1 by 2. That is minus 1 by 2. That is equal to 4 by 2 is 2. Minus 2, 0, 0, minus 4. This is the diagonalized. A cap is diagonal. We got from P matrix. That's all about this sum. So we found eigenvalues, eigenvectors, and then diagonalize the A matrix. Equations using Laplace transform. Let x dot equal to ax plus bu be the state equation. Its output equation y equal to cx plus du, where a, b, c, and d are matrices. Let us take this and take Laplace transform. We will get s x of s minus x of 0 equal to a x of s plus b u of s. If we combine all x of s together, we will get si minus a, where I is the identity matrix. X of s equal to x of 0 plus b u of s. Multiply on both sides by si minus a inverse. You will get x of s equal to si minus a inverse x of 0 plus si minus a inverse b u of s. You will get. If you take Laplace inverse on both sides, you will get x of t state variable equal to Laplace inverse of si minus a inverse x of 0 plus Laplace inverse of si minus a inverse b u of s. So let this is a solution. This is a solution for state equation. Let si minus a inverse equal to si minus a inverse equal to pi of s. This is called state transition matrix. State transition matrix. Then the equation becomes x of t equal to Laplace inverse of phi of s x of 0 plus Laplace inverse of phi of s b u of s. B u of s. That's all. This is a solution for given state equation. A linear time invariant system is characterized by the state equation x1 dot x2 dot equal to A matrix 1 0 1 0 1 1 state variable plus B matrix multiplied by U, where U is a unit step function. Compute the solution of this equation assuming initial condition. In transfer function method, we cannot use the initial condition, but here we can use the initial condition. Use inverse Laplace transform technique. So for that, the first step, what is the solution? X of t equal to we have to find x of t. That is the solution. Because x dot is given, we have to find x of t. This is x dot of t. This is x dot. We have to find x of t equal to Laplace inverse of phi of s by x of 0 plus Laplace inverse of phi of s b u of s. That's all. So we have to find phi of s. Phi of s equal to what? Si
minus A inverse, that is equal to SI means what you will write S 0 0 S, that is SI minus A. A is 1 0 1 1. So what inverse, that is equal to S minus 1 0 0 minus 1, therefore minus 1 and S minus 1 inverse, that is equal to 1 by determinant of this, that is adjoint matrix by, that is equal to adjoint matrix by determinant. Determinant of this is 1 by S minus 1 whole square. The adjoint matrix can be found by, since it is 2 by 2 matrix, we have to interchange diagonal elements. Same, that's why we can write as such. Interchange the diagonal elements and change the sign of half diagonal elements. That's all. So we got SI minus A inverse. If we bring this inside, what you will get? 1 by S minus 1 0 1 by S minus 1 whole square 1 by S minus 1. So we can substitute that 1 by S minus 1 0 1 by S minus 1 whole square 1 by S minus 1. X of 0 is given. X of 0 is 1 0, it is given. So we can substitute 1 0 here plus Laplace inverse of phi of S 1 by S minus 1 0 1 by S minus 1 whole square 1 by S minus 1 B matrix is 0 1. U is, it is mentioned that is step function, therefore U is 1 by S. That's all. That's all. So first we have to multiply these two. If you multiply these two, Laplace inverse of, if you multiply first row, first column, you will get 1 by S minus 1. Take second row, first column, you will get 1 by S minus 1 whole square plus, if you multiply these two, take first row, first column, you will get 0. Take first row, first column, you will get 0. Second row, first column, you will get 1 by S minus 1. Multiplied by 1 by S. 1 by S, before that Laplace inverse, that is equal to, if you multiply this by 1 by S, you will get the denominator S into S minus 1. Here you will get 0. So this we can multiply by S and we can remove this. So what is the solution? X of t equal to Laplace inverse of 1 by S minus 1, 1 by S minus 1 whole square plus Laplace inverse of 0, 1 by S multiplied by S minus 1. We have to do the partial fraction here. That's why if you find the Laplace inverse for this, that is 1 by S plus A, Laplace inverse of 1 by S plus A equal to e power minus AT. Therefore, for this, what you will get? E power 1t. Here is 1 by S multiplied by S plus A whole square. Laplace inverse of S plus A whole square equal to t e power minus AT. So therefore you will get e power t plus Laplace inverse of This we can write as A by S plus B by S minus 1. We have to find A and B. A is equal to 1, B equal to 1. 1 by S multiplied by S plus S minus 1 multiplied by S, where S equal to 0, you will get minus 1. B equal to 1 by S multiplied by S minus 1 multiplied by S minus 1, where S equal to 1, that is equal to 1. Therefore, this equation becomes e power t e power t plus Laplace inverse of minus 1 by S plus 1 by S minus 1. So if you take Laplace inverse, you will get e power t e power t plus 0 minus 1. Laplace inverse of 1 by S is minus 1. Minus 1 by S is minus 1. For this plus e power t, that is equal to, if you add these two together, what you will get is e power t minus 1 plus 1 plus t into e power t. Here minus 1 plus e power t is common if we take t plus 1. So this is the solution of given state model. This is the solution of given state model. This is the solution of given state equation.
The state space model B, x dot equal to ax plus b, and the output equation y equal to cx plus d. Take the first transform on both sides, you get s x of s minus x naught equal to a x of s plus b u of s. To bring x of s one side, you will get si minus a x of s equal to x naught plus b u of s, or x of s multiply on both sides by si minus a inverse. 3 multiplied by si minus a inverse, you will get x of 0 plus si minus a inverse b u of x. To find transfer function, let us assume that 0 initial condition. That is, x of 0 is 0 matrix, null matrix. Therefore, x of s equal to si minus a inverse b u of s. That will be 1. Therefore, now let us consider this y equal to cx plus d. Substitute this. First, let's take the Laplace transform. Y of s equal to cx of s plus d u of s. So if you substitute 1 in 2, you will get c si minus a inverse b u of s plus b u of s. Therefore, y of s upon u of s, this is the transfer function, p of s equal to, we bring this u of s, we bring this u of s to the left hand side, you will get c si minus a inverse b plus b. That's all. This is the transfer function. This is a derivation for transfer function. Therefore, for a given transfer function, how to find the transfer function from state model E of S transfer function C matrix multiplied by Si minus A inverse B plus D. That is equal to C phi of S. We can call Si A minus inverse can be called as phi of S B plus D. Find the transfer function for the given state. Find the transfer function for the given state space system. Here A equal to minus 2, 0, 0, minus 1. B equal to 0, 1. C equal to 1, 2. D equal to null matrix. Therefore, phi of S equal to Si minus A inverse. That is equal to 2 by 2 matrix. Therefore, Si equal to S 0, 0 S minus A equal to minus 1, 0, 0 minus inverse. That is equal to S plus 1, 0, 0, S plus 2 inverse. That is equal to the determinant of this matrix is 1 by S plus 1 multiplied by S plus 1. And the adjoint matrix is interchange the diagonal elements S plus 2, S plus 1. We will change the sign of the off diagonal elements. So this is the inverse. So the phi of S we got. What is transfer function? P of S equal to C phi of S B plus G. C phi of S B plus D. D equal to null matrix. This is a null matrix. Therefore, the transfer function is C. C matrix is 1, 2. This write one more step here. If you bring on this inside, if you bring this inside, what you will get is 1 by S plus 1, 0, 0, 1 by S plus. So substitute this phi of S here, you will get 1 by S plus 1, 0, 0, 1 by S plus. B matrix is 0, 1. This is what is the dimension of this? 1 by 2. This is 2 by 2. This is 2 by 1. Therefore, the final answer will be 1 by 1 transfer function. So, you take first row, first column, you will get you will get 1 by S plus 1. Take first row, second column, you will get 2 by S plus 1. Multiplied by 0, 1. That is equal to 2 by S plus 1. If you have any doubt, you can come type in the comment section, or if you want any topic to be covered, that also you can mention in the comment section. Thank you. The system x dot equal to ax plus mu and y equal to cx plus mu is said to be completely controllable. if there exists an input vector, u of t, which transfer the system from initial state x of t naught to a desired state t. You want to transfer a system from one state to another state. This is the t naught. This is at tf. You want to transfer the system from this state to this state means if a u is available to transfer from this state to this state means then the system is said to be controllable. How to understand the controllable system and observable system? Example for observable system is the moon is an observable system. You cannot control it. The rotation of the earth is observable system. You cannot control it. The sun is an observable system. You cannot control it. Similarly, the system we design may be controllable or observable. Completely controllable means all state variables, x1, x2, etc., xn, all are controllable means then the system is said to be completely controllable. Otherwise, partially controllable. Suppose you cannot control xn, yeah, x through xn minus 1 you can control means it's not completely controlled. Similarly, if we can observe x1, x2, etc., xn, then the system is said to be completely observable. Here, what is the test for a system to be completely controllable? For that, this is the test for a system to be completely controllable. The QC matrix is B, AB, A square B. This is a matrix, etc. A n minus 1 B, A to the power n minus 1 because the nth order system. B, this is the composite matrix. Composite matrix is the rank of this composite matrix QC is equal to n, where n is the order of the system. Then the rank of composite matrix is n. The system is said to be completely controlled. Similarly, observability. If a system has a n state variable, x1, x2, x3, etc., all n states are observable means it should pass this test. The composite matrix Q naught equal to C, CA, CA square, etc., CA power n minus 1. This composite matrix, the rank of this composite matrix Q naught must be equal to n. That is order of the system. That is equal to n. That is equal to order of the system. Then the system is said to be completely controllable. A linear time invariant system is characterized by the state variable model. Comment on the controllability and the observability of the system. Here, A matrix minus 1, 0, 0, minus 2. B matrix equal to 0, 1. C matrix equal to 1, 2. Now let us form the controllability composite matrix. QC equal to B, AB. Only 2 because its order is 2. A power n minus 1. 2 minus 1 is 1. We have to stop here because the order is 2. Order is 2. QC equal to this. This is equal to what is B? 0, 1. What is AB? AB equal to A is minus 1, 0. 0 minus 2. B is 0, 1. Take first row, first column, you will get 0. take second row, first column, you will get -2. This is A. So if you substitute 0, -2, this is QC matrix. What is the rank of this? Rank of QC equal to 1, because the determinant of QC equal to 0. What is the definition for rank of a matrix? Rank of a matrix. Order of largest non-singular sub-square matrix. This is the rank of the matrix. Order of largest non-singular sub-square matrix. What is the largest sub-square matrix? 2 by 2. It is not non-singular, singular, because its determinant is 0. Therefore, lower than that is 1 by 1 matrix, single element matrix. That is non-singular, because 1 is there, -2 is there. Therefore, rank is 1. Therefore, it is not completely controlled. What about observability? Q not observability equal to CA, because it is 2 by 2. Second order system. That's why only what is C? C is 1, 2. CA equal to what? CA equal to 1, 2. A equal to -1, 0, 0, -2. Take first row, first column, you will get -1. Take first row, second column, you will get -4. Substitute here, -1, -4. The determinant of Q naught equal to -4 plus 2 equal to -2. Not equal to 0. Therefore, rank of largest non-singular sub-square matrix is 2 by 2. Therefore, rank of Q naught equal to 2. Hence, it is that is equal to n. That is equal to n. Hence, it is completely controlled. Completely controlled. Completely observed. Completely observed. Is equal to n. The rank of Q naught equal to 2 equal to n. Therefore, it is completely observed. But here, its rank is rank of QZ is 1, less than 2, less than n, less than n. Therefore, it's not completely controlled. That's all about state variable analysis. This is the final part. If you have any doubt, you can type in the comment section, or if you want any topic to be covered, that also you can mention in the comment section. Thank you.